What happens when an object older than Earth itself passes through our solar system, carrying chemistry from a sun we'll never see? In the summer of 2025, astronomers discovered something that would make them ask uncomfortable questions about how well we actually know the cosmic neighborhood we call home. Silence wraps around the outer edges of our solar system like a blanket woven from darkness itself. Out where sunlight barely whispers and the cold is absolute, something drifts through the void with patient inevitability. It moves without sound, as all things do in that cathedral of emptiness, carrying with it a story older than human memory, older than the ground beneath your feet. Its designation in the catalog of human discovery reads simply as 3IATLAS, but names are fragile things when applied to objects that have witnessed suns we will never see. If you find yourself drawn to this mystery, let your curiosity settle gently into these words. There is no urgency here, no need to rush toward conclusions. The universe unfolds at its own pace, and tonight we follow that rhythm together. As you listen, perhaps you'll share where you are in this moment. What thoughts drift through your mind as sleep approaches? What questions linger about the nature of things that travel between stars? The discovery arrived not with fanfare, but with patient observation, as most cosmic revelations do. On a summer night in 2025, automated telescopes in Chile were conducting their eternal vigil, watching for fragments of rock and ice that might one day threaten our world. The ATLAS system, designed to protect rather than to wonder, captured light from something that would challenge every comfortable assumption about our place in the galactic neighborhood. At first, it seemed unremarkable, another faint smudge moving against the background stars. The astronomers who first noticed it logged the detection with practiced efficiency, expecting nothing more than another routine comet, one of countless icy wanderers that loop through our solar system on predictable paths carved by gravity's patient hand. But numbers began to tell a different story, and numbers, unlike emotions, do not lie or embellish. The mathematics of celestial motion are ancient and reliable, equations that have guided sailors and satellites alike. When astronomers calculated the path of this new visitor, something fundamental shifted in the data. The trajectory refused to close into an ellipse, refused to bend back toward the sun that should have captured it in gravitational embrace. Instead, the curve opened outward, hyperbolic, carrying the unmistakable signature of an object that had come from elsewhere and would return there when its brief passage through our neighborhood concluded. This marked it as interstellar, the third such confirmed visitor in human history. The first, Oumuamua, had arrived in 2017 like a cipher written in motion, its elongated form and strange acceleration sparking debates that still echo through scientific literature. The second, Comet Borisov in 2019, had been more familiar, more comfortable, behaving as comets should. Now came 3IATLAS, and with it, new questions that resist easy answers. Let your breathing slow as we consider what it means for something to arrive from between the stars. The distances involved mock human comprehension. Light itself, traveling at speeds our vehicles cannot approach, requires years to cross the gulfs that separate stellar systems. For a physical object made of matter and subject to the patient drag of time, the journey demands not years but ages, epochs during which entire civilizations might rise and fade to memory. 3IATLAS had been traveling for longer than we know, propelled by forces applied in a stellar nursery we will never observe, carrying in its frozen composition a chemical record of environments alien to our experience. It entered our solar system moving at nearly 60 kilometers per second, fast enough to escape the sun's gravitational well after its brief visit, fast enough to suggest the immense distances it had already traversed. The initial estimates placed it far from the sun when first detected, out near Jupiter's orbital distance where light is weak and temperatures approach the edge of absolute cold. At that distance, most comets remain dormant, their ices locked in eternal winter. But even then, observers noticed something unexpected. As more data accumulated from telescopes around the world, each adding their observations to a growing mosaic of understanding, patterns emerged that didn't quite fit the templates of familiar cometary behavior. Brightness fluctuated in ways that seemed almost deliberate, rising and falling with rhythms that resisted simple explanation. The spectrum of light reflected and emitted carried signatures of molecules that appeared in unusual proportions, carbon dioxide dominating where water vapor should have been more prominent. These weren't violations of natural law, but they were deviations from expectation, whispers that this visitor played by rules shaped under different stellar conditions. Word spread through the astronomical community with the speed of electronic communication. Observing time on major telescopes, usually allocated months in advance through competitive proposals, was suddenly redirected. The Hubble Space Telescope, orbiting above Earth's atmospheric distortions, turned its unblinking eye toward this enigmatic traveler. What it captured would fuel discussions that continue as you listen to these words in the quiet of your evening. The images showed a faint glow surrounding the nucleus, that characteristic coma of gas and dust that marks active comets. A tail began to form, though fainter than predictions suggested, pointing away from the sun as solar radiation pushed particles outward. But there were complications, anomalies in the details that made veteran comet observers pause and reconsider their assumptions about what they were witnessing. Some observers noted what appeared to be a secondary tail, an anti-tail as it's known in the technical literature, pointing in an unexpected direction. This phenomenon, while not unknown in cometary science, added another layer of intrigue to an already complex picture. The physics of how dust and gas interact with solar radiation and the solar wind can produce such features, but their appearance in 3IATLAS seemed particularly pronounced, as if the object was shedding material in ways that standard models struggled to fully capture. Dr. Sarah Chen, working at the California Institute of Technology's Planetary Science Division, coordinated observations from multiple instruments, building a timeline of the object's evolution as it fell deeper into the sun's gravitational well. Her team tracked changes in brightness, measured the composition of the coma through spectroscopy, and attempted to constrain the size of the hidden nucleus beneath its glowing veil. Each measurement brought new data, but also new puzzles that existing frameworks couldn't quite accommodate. The size estimates proved particularly elusive. Initial calculations, based on how much sunlight the object reflected, suggested something enormous, perhaps tens of kilometers across. But these calculations assumed a certain reflectivity, a certain ratio of solid surface to glowing gas. As more detailed observations accumulated, particularly from infrared instruments that could peer through some of the obscuring dust, The estimated size shrank dramatically. The nucleus might be only a few kilometers wide, perhaps even smaller, though uncertainty remained substantial. This matters because size connects directly to mass, and mass determines how much material the object can shed before disintegrating entirely. Comets are fragile assemblages held together by gravity barely stronger than the touch of a hand on paper. They fragment, they crumble, they dissolve in the sun's heat like frost in morning light. For 3IATLAS, the question of structural integrity would become increasingly relevant as its journey continued. As September gave way to October, the visitor approached its moment of greatest stress. Perihelion, that closest approach to the Sun, was scheduled for October 31st, 2025. At that point, 3IATLAS would pass approximately 1.4 astronomical units from our star, placing it roughly between Earth's orbit and Mars's more distant path. The heating would intensify, driving sublimation of ices, potentially cracking the nucleus through thermal stress and differential expansion. Astronomers prepared for this critical window with careful planning. Multiple observatories coordinated their schedules, ensuring continuous coverage as the object rounded the Sun. The European Space Agency's solar orbiter, though not designed for cometary observations, found itself positioned to potentially capture unique perspectives. Mars orbiters were alerted and prepared, as 3IATLAS would pass remarkably close to the red planet on October 3rd, offering an unprecedented opportunity for detailed imaging from relatively nearby. But then, something unexpected occurred that would change the narrative entirely. Before the object could reach perihelion, before it could pass through that moment of maximum solar heating, its behavior shifted in ways that demanded explanation. The brightness increased more rapidly than models predicted, then plateaued, then surged again in patterns that seemed almost rhythmic. Spectroscopic observations showed the chemical composition of the coma evolving in unexpected ways. Some astronomers began to notice what appeared to be multiple condensations within the coma, bright spots that might indicate fragmentation of the nucleus. This is not unusual. Many comets break apart under solar stress. But the pattern of these fragments, if fragments they were, didn't quite match previous observations of disintegrating comets. They seemed to maintain coherence longer than expected, moving in ways that suggested something beyond simple gravitational dynamics. It was at this juncture that speculation began to intensify beyond the usual bounds of astronomical discourse. Dr. Abraham Loeb, a respected astrophysicist at Harvard with a documented interest in the possibility of extraterrestrial technology, published a paper examining 3IATLAS through an unconventional lens. His analysis, conducted with careful mathematical rigor, explored whether the object's trajectory and behavior might be consistent with artificial origin. The paper noted several features that, while not proof of anything extraordinary, were statistically unusual. The alignment of the object's path with our solar system's ecliptic plane, the geometry of its closest approaches to multiple planets, the timing of its passage through the inner solar system, all these factors, when combined, produced probability values that were low enough to warrant consideration of alternatives to the natural comet hypothesis. To be clear, Loeb and his colleagues did not claim certainty. Science rarely offers such luxury when dealing with unique events. Instead, they proposed this as a thought experiment, a way of exploring the boundaries of what observations could rule out or support. The methodology was sound, even if the conclusion struck many as premature. But in the modern information ecosystem, nuance often gets lost between the initial publication and its propagation through media channels. Headlines simplified the message, as headlines must. Harvard scientists suggest alien probe captures attention more effectively than astrophysicist proposes alternative hypothesis requiring further data to constrain. The public response divided between fascination and skepticism, with many people asking whether science had finally found evidence of intelligence beyond Earth, while others dismissed the entire discussion as sensationalism masquerading as inquiry. The truth, as often happens in science, resided in the careful middle ground between dramatic extremes. 3IATLAS was neither a mundane chunk of ice behaving exactly as predicted, nor was it a spacecraft broadcasting its artificial nature through obvious technological signatures. It was something more interesting and more subtle, a natural object from another stellar system, carrying in its composition and behavior the fingerprints of formation conditions, unlike those that shaped our familiar solar system comets. The carbon dioxide dominance in its coma provided a crucial clue. In our solar system, comets that formed in the outer reaches tend to be rich in water ice, with carbon dioxide as a secondary component. But stellar systems vary in their chemistry based on the composition of the molecular cloud from which they condensed, the temperature gradients in their protoplanetary disks, and the timing of planet formation processes that can scatter or concentrate various volatile species. A star system with different initial abundances might produce comets where carbon dioxide is the primary ice, with water as the minor constituent. This isn't exotic physics, it's simply chemistry, playing out under different initial conditions. The ratios of elements in interstellar space vary by location and epoch. A comet born in a region where carbon was more abundant relative to oxygen would naturally incorporate this bias into its frozen composition. As 3IATLAS approached perihelion, this unusual chemistry manifested in observable ways. The sublimation of carbon dioxide ice occurs at slightly lower temperatures than water ice, meaning the comet became active at greater distances from the Sun than water-dominated comets typically do. This could explain some of the brightness variations, not evidence of artificial propulsion, but natural response to solar heating in a body with chemistry shaped by an alien sun. October 3rd arrived with its promised Mars encounter. At closest approach, 3IATLAS passed approximately 29 million kilometers from the red planet, close enough in cosmic terms that the fleet of orbiters and rovers humanity has stationed there could observe it with instruments never designed for such opportunities. The European Space Agency's ExoMars Trace Gas Orbiter, the UAE's Hope Probe, NASA's Mars Reconnaissance Orbiter, all turned their attention skyward, capturing images and spectra of the visitor. The data from these observations would take weeks to fully analyze, but preliminary reports confirmed what Earth-based telescopes had been seeing: a comet in the throes of active sublimation, shedding gas and dust as solar radiation warmed its ancient ices. The tail, now more prominent, streamed behind it, and the coma had expanded to encompass hundreds of thousands of kilometers. From Mars's perspective, it appeared as a faint but distinct smudge against the star field, growing brighter as October progressed. Meanwhile, on Earth, amateur astronomers joined the professional observation campaigns. Equipped with modern CCD cameras and modest telescopes, these dedicated observers contributed valuable data, filling gaps in coverage when professional facilities were engaged with other programs or weather interfered with observations. Their images, shared freely across internet forums and social media platforms, provided continuous monitoring that no single institution could match. The collaborative nature of this observation campaign represented something profound about modern astronomy. No longer was cosmic discovery the exclusive domain of professionals with access to the largest telescopes. The democratization of technology had created a global network of observers, each contributing pieces to a puzzle that no one could solve alone. In quiet backyards and on remote hilltops, people pointed their instruments skyward and gathered photons that had traveled unimaginable distances to reach human eyes. As October wore on, the evidence against the artificial hypothesis accumulated steadily. Every new observation reinforced the interpretation of 3IATLAS as a natural, if unusual, interstellar comet. The tale grew in precisely the manner that models of sublimating ice predicted. The spectrum evolved as different volatile species became active at different temperatures. The brightness variations, once thought mysterious, could be explained by the irregular shape of the nucleus and the uneven distribution of volatile ices across its surface. The fragments or condensations noted in the coma were consistent with natural fragmentation processes. Comets often shed pieces as thermal stress creates fractures, as subsurface pockets of volatile ice suddenly vent, or as weak gravitational bonds prove insufficient to hold loosely consolidated material together. Detailed imaging showed these fragments following ballistic trajectories, their paths determined purely by the velocity at which they were ejected and the gentle tug of solar gravity. By late October, as 3IATLAS approached its scheduled perihelion passage, the astronomical community had reached a working consensus. This was not a probe from another civilization conducting reconnaissance of our solar system. It was something equally remarkable but more accessible to scientific understanding. A pristine sample of matter from another star's planetary system, offering a rare opportunity to study the composition and structure of material formed under different conditions than those that prevailed in our own cosmic neighborhood. The distinction matters. The alien hypothesis, while attention-grabbing, would have been nearly impossible to definitively prove with available observations. How would one distinguish between a derelict probe tumbling through space for millions of years and a natural object with unusual but explicable properties? Without close-up examination, without the ability to detect artificial structures or signals, the question would remain perpetually ambiguous, an interesting thought experiment, but scientifically unresolvable. The natural comet interpretation, by contrast, opened doors to specific scientific questions with achievable answers. What was the nucleus composition? How did the dust grain size distribution compare to solar system comets? What isotopic ratios could be measured in the sublimating gases, offering clues about the temperature and pressure conditions during its formation? These questions could be addressed through spectroscopy, photometry, and modeling, tools astronomers had refined over decades of studying cometary visitors. As October 31st approached, telescopes around the world prepared for the perihelion passage. This would be the moment of maximum activity when solar heating reached its peak and the comet's nucleus would face its greatest stress. Would it survive intact, or would it disintegrate into a cloud of fragments like so many comets before it? The answer would provide crucial constraints on its internal structure and strength, parameters that in turn would inform understanding of how interstellar objects survive their journeys through the galaxy. But perihelion presented an observational challenge. From Earth's perspective, 3I-ATLAS would pass nearly behind the Sun, its position in the sky making ground-based observations extremely difficult or impossible during the most critical days. Space-based assets offered some relief from this geometric constraint, but even they faced limitations. The Sun's brightness overwhelms nearby objects, creating a glare that obscures faint comets, unless specialized equipment blocks the solar disk. This meant there would be a gap in continuous coverage, a window of several days when humanity's understanding of 3I-ATLAS would rely on interpolation rather than direct observation. What the comet did during this hidden passage would only become clear when it emerged on the far side of the Sun, when telescopes could once again track its position and measure its properties. The uncertainty during this period would prove fertile ground for continued speculation. November arrived with 3I-ATLAS beginning its outbound journey, having survived perihelion intact. As it re-emerged from solar conjunction, observers confirmed that the nucleus remained coherent, still shedding gas and dust, but showing no signs of catastrophic fragmentation. The tail, now at its most spectacular, stretched across millions of kilometers, a testament to the material being liberated from ancient ices as they experienced starlight for perhaps the first time since the object's formation. The December closest approach to Earth, while still distant at 1.8 astronomical units, provided excellent viewing conditions. Amateur and professional astronomers alike captured images showing the comet's graceful arc across the stellar background. The coma glowed with a faint green tint, a color produced by diatomic carbon molecules excited by solar ultraviolet radiation. This, too, was perfectly normal cometary behavior, chemistry playing out as textbooks predicted. As the year drew toward its close, 3I-ATLAS began its inexorable fade, receding from the Sun, moving back toward the outer solar system on its hyperbolic trajectory. The comet's activity declined as temperatures dropped and sublimation slowed. The tail thinned, the coma contracted, and the nucleus once again retreated into dormancy. By early 2026, it would be too faint for all but the largest telescopes to track. By mid-year, it would effectively disappear from human observation, carrying its secrets back into interstellar space. What remains, now that the visitor has passed beyond our instrument's reach, is a richer understanding of the diversity of small bodies in our galaxy. 3I-ATLAS demonstrated that interstellar comets can have compositions significantly different from their solar system cousins, reflecting the variety of formation conditions across different stellar systems. This observation alone justified the intensive observation campaigns. But beyond the specific scientific findings, the passage of 3I-ATLAS illustrated something about human nature and our relationship with the unknown. The eagerness to interpret anomalous observations as evidence of intelligence, the rapid spread of simplified narratives through media ecosystems, the tension between caution and speculation in scientific discourse. These patterns reveal as much about us as any measurements of the comet revealed about its nature. Perhaps this is inevitable. We are pattern-seeking creatures, evolved to detect agency and intention in the world around us. This cognitive tendency served our ancestors well, making them alert to predators hidden in underbrush, to the intentions of rivals and allies. But it also makes us prone to seeing design where only chance and natural law operate, to interpreting the unfamiliar as the intentional rather than simply accepting our own ignorance. The scientist's discipline involves resisting this tendency, maintaining skepticism even toward appealing hypotheses, demanding extraordinary evidence before accepting extraordinary claims. Yet scientists are human too, subject to the same cognitive biases, the same longings for discovery that would secure their place in history. The alien hypothesis represents the most extraordinary discovery imaginable, confirmation that intelligence has arisen elsewhere in the cosmos, and the temptation to interpret ambiguous data in its favor is powerful. What 3IATLAS ultimately teaches, then, is humility. Humility about the limits of what we can know from distant observations, about the provisional nature of scientific conclusions, about the vast space between speculation and proof. The comet came and went, and we learned from it, but much remains mysterious. Its exact origin system, the circumstances of its ejection into interstellar space, the full inventory of its composition. These questions may never be answered completely. And perhaps that is appropriate. The universe is under no obligation to satisfy our curiosity completely. It offers glimpses, fragments, partial revelations that must suffice while we build understanding slowly, observation by observation, generation by generation. 3IATLAS was one such glimpse, a window briefly opened onto the processes that shape small bodies in other stellar systems, then closed again as the visitor receded beyond the reach of our instruments. The story, however, doesn't end with the object's departure from our observable sphere. The data collected during those intensive months of observation will fuel research papers for years to come. Graduate students will write dissertations analyzing specific aspects of the comet's behavior. Theorists will refine their models of cometary activity to account for the unusual chemistry. And always, in the background, will linger the question, what else might be drifting through the darkness between stars, waiting for chance to bring it close enough for us to notice? The statistics suggest we should expect more interstellar visitors now that our detection capabilities have improved. 3IATLAS was the third confirmed, but it likely won't be the last. Each new detection will bring its own set of surprises, its own deviations from expectation, because objects from other stellar systems formed under conditions we can only infer from distant observation. Every visitor is a messenger, carrying information encoded in its composition, its structure, its behavior under solar heating. Some of these future visitors may prove even more anomalous than 3IATLAS. Perhaps one will show evidence of complex organic chemistry, molecules associated with life's building blocks, raising questions about panspermia and the spread of biological potential through the galaxy. Perhaps one will exhibit truly inexplicable behavior that resists interpretation through known physics, forcing a genuine crisis in our understanding. Or perhaps they will all be, like 3IATLAS, fascinating but ultimately natural objects that expand our knowledge without overturning fundamental assumptions. The public reaction to 3IATLAS also offers lessons worth considering. In an age of instant communication and algorithmic amplification, sensational narratives spread with remarkable speed. Claims that might once have remained confined to specialized publications now reach millions within hours, often stripped of nuance and qualification. Harvard scientist says alien probe carries more viral potential than researcher explores alternative hypotheses within Bayesian framework, even when the latter more accurately represents the actual work. This creates challenges for science communication. How does one maintain intellectual honesty about uncertainty while also being heard above the noise of confident but unfounded claims? How does one preserve the tentative, provisional nature of scientific conclusions when media incentives favor definitive statements? These questions don't have easy answers, but they become increasingly important as scientific findings become more accessible to broader audiences. The role of scientific authority also comes into question. When a respected researcher at a prestigious institution proposes an unconventional hypothesis, their credentials lend weight to the claim regardless of how speculative it might be. This can be beneficial, protecting unconventional ideas from premature dismissal, but it can also mislead non-specialists into believing there's more consensus behind a fringe interpretation than actually exists within the expert community. In the case of 3IATLAS, the overwhelming majority of planetary scientists and comet specialists concluded early on that the natural comet interpretation was sufficient and most parsimonious. The alien hypothesis, while not technically impossible to disprove, required invoking extraordinary explanations for observations that conventional comet physics could already explain. Occam's razor, that principle which favors simpler explanations when they fit the data equally well, firmly supported the natural origin conclusion. Yet the alien hypothesis persisted in public discourse long after the scientific community had moved on. This persistence reveals something about human psychology and our relationship with the possibility of extraterrestrial intelligence. We want to believe we're not alone in the universe. The thought of intelligent life elsewhere, even if manifested only through ancient probes rather than active communication, would fundamentally change our sense of cosmic context. This longing is not irrational or childish. It reflects genuine questions about the frequency of intelligence in the universe, questions with profound philosophical implications. If intelligence is common, then the universe is fundamentally different than if we are alone or nearly so. The search for biosignatures and technosignatures represents legitimate scientific inquiry, and occasional false alarms are inevitable when searching for signals that would be among the most important discoveries in human history. The key is maintaining appropriate skepticism while remaining open to evidence. 3IATLAS demonstrated that this balance is difficult to achieve, especially in real time as observations accumulate and interpretations evolve. The early data, taken in isolation, could support multiple hypotheses. Only with patient accumulation of observations could the natural interpretation be established with confidence. But patience is scarce in modern information ecosystems that reward speed and certainty over careful deliberation. As you drift toward sleep, perhaps you can appreciate the complexity of this situation. The universe is both more wondrous and more subtle than simple narratives allow. 3IATLAS was not an alien spacecraft, but it was still remarkable, a visitor from another star, carrying in its icy nucleus a record of conditions in a stellar nursery we will never observe directly, now returning to the interstellar depths after its brief passage through our cosmic neighborhood. The chemical story written in 3IATLAS's coma speaks to formation conditions around a star whose properties we can only infer. The dominance of carbon dioxide over water suggests either a colder formation region than typical for solar system comets, or a different ratio of carbon to oxygen in the protoplanetary disk. Both scenarios are plausible and not mutually exclusive. The star might have been cooler than our Sun, pushing the frost line, that boundary where different volatiles freeze, closer to the stellar center. Or the molecular cloud from which the system formed might have been enriched in carbon through previous generations of stellar nucleosynthesis. Isotopic measurements, though difficult to obtain with high precision for such a faint object, hinted at ratios distinct from solar system norms. The deuterium to hydrogen ratio in water molecules, when measurable, provides a thermometer for formation conditions. Higher ratios suggest colder temperatures during ice formation. The carbon isotope ratios tell stories about nucleosynthetic processes in the stars that enriched the molecular cloud before it collapsed to form planets and comets. Each measurement is a clue, though the puzzle remains incomplete. The dust grains shed by 3IATLAS also carried information, encoded in how they scattered sunlight. Particle size distributions affect the polarization of reflected light, the way brightness changes with phase angle, the angle between sun, comet, and observer. Detailed modeling of these optical properties suggested dust grains somewhat larger than typical for active solar system comets, though uncertainty bands remained wide enough that this conclusion stayed tentative. These grains were themselves aggregates of smaller particles, loosely bound by cohesive forces between irregular surfaces. In the cold of interstellar space, they had remained essentially unchanged for billions of years, preserving the conditions of their original condensation from vapor in the protoplanetary disk. Now, liberated by solar heating, they drifted outward on solar radiation pressure, some eventually to be captured by Earth's atmosphere as micrometeorites, unrecognizable among the cosmic dust constantly raining down upon our world. Consider for a moment the journey these grains had taken. Formed around another star in an era when our solar system might not yet have existed, incorporated into a growing comet nucleus through gentle collisions in a debris disk, then ejected, perhaps through gravitational perturbations from a migrating planet, or tidal forces during a close stellar encounter, into interstellar space. For millions or billions of years, they traveled through near-perfect vacuum, occasionally encountering stray atoms of hydrogen or helium, but otherwise completely isolated from matter or energy. Then, by chance, they entered our solar system, fell into the sun's gravitational well, experienced heating for the first time in ages, and finally were liberated from the nucleus to begin a new journey. Some would spiral into the sun, some would be blown outward into interstellar space by radiation pressure, and a few might eventually encounter planets, ending their journey in a brief flash of heat as they vaporized in an atmosphere. Each grain's voyage was unique, yet all shared this common history of formation elsewhere, long travel, and brief awakening in our sun's light. The nucleus itself, that solid core hidden beneath the glowing coma, remained largely mysterious. Even the best images showed only an unresolved point of light. the nucleus too small and too obscured by its own outgassing to reveal surface features or shape. Size estimates ranged from 3 to 7 kilometers in diameter, depending on assumptions about how reflective the surface was and how much of the observed brightness came from reflected sunlight versus light scattered by the coma. Computer models attempted to reconstruct the nucleus properties from observable consequences. The amount and composition of gas being released, combined with theories of ice sublimation, constrained the temperature and composition of the surface layers. The non-gravitational forces detected in the orbital solution, those tiny pushes from asymmetric outgassing acting like rocket thrusters, provided information about where on the nucleus the jets were located and how they oriented the object's rotation. These jets, fountains of gas and dust escaping from the nucleus, occur when solar heating penetrates the surface layers and vaporizes buried ice. The vapor pressure builds until it overcomes the weak cohesive forces holding the surface material together, and a geyser erupts, often carrying dust grains along with the gas. These jets can be highly directional, focused by the topography of the surface, perhaps escaping through fissures or from the walls of impact craters, where the overlying dust has been blown away. For 3IATLAS, the jet activity seemed concentrated on the sunward hemisphere, as expected, but with asymmetries that suggested an irregular shape and non-uniform composition. Perhaps one region of the nucleus was richer in volatile ices, while another was more depleted or covered with a thicker layer of insulating dust. Such heterogeneity is common in solar system comets, and presumably in interstellar ones as well. The rotation of the nucleus, though not directly observed, could be inferred from periodic variations in brightness and gas production. The object likely tumbled rather than spinning smoothly around a single axis, its rotation state altered by the torques from asymmetric outgassing. Over time, these torques can spin up or spin down a comet, can change its rotation axis orientation, can even lead to fragmentation if internal stresses exceed the weak structural strength. As 3IATLAS rounded the Sun and headed back toward the outer solar system, its activity began to decline. The decreasing solar energy input meant less heating, less sublimation, weaker jets. The coma contracted, the tail faded, and eventually the object returned to the dormant state it had maintained for most of its existence. By the time it crossed back beyond Jupiter's orbit, it would once again be a cold, dark, silent fragment of ice and rock, indistinguishable at a distance from the countless other small bodies drifting through the galaxy. But before that final fade occurred, there was one more chapter in the 3IATLAS story that deserves reflection. Throughout November and December, as the comet traced its outbound path, scientific papers began appearing in journals and on preprint servers, documenting the observations and analyses conducted during the intensive observation campaigns. Each paper addressed a specific aspect: the photometry, the spectroscopy, the orbital dynamics, the dust properties, building collectively toward a comprehensive portrait of the visitor. Reading these papers reveals the careful, methodical nature of astronomical research, so different from the breathless headlines that characterized public discussion. Each conclusion was hedged with appropriate uncertainty, each measurement accompanied by error bars quantifying the precision. Multiple independent teams analyzed the same data using different techniques, and when their results agreed, confidence increased. When they disagreed, Additional observations or refined models were needed to resolve the discrepancy. This is science as it actually functions, not the caricature of sudden breakthroughs and unshakable certainty. Progress comes through accumulation of evidence, through gradual refinement of understanding, through the slow process of building consensus as the weight of data tilts toward particular interpretations. It lacks the drama of discovery myths, but it produces reliable knowledge, provisional always but increasingly robust as multiple lines of evidence converge. The conclusion that 3I-ATLAS was a natural interstellar comet, not an artificial probe, emerged from this process. No single observation proved it definitively, but the totality of evidence, the spectroscopy showing normal cometary molecules, the brightness variations consistent with sublimating ice, the structural integrity matching cometary nuclei, the trajectory following purely gravitational and outgassing forces, all pointed toward the same interpretation. Alternative hypotheses, including the artificial origin possibility, remained technically viable only by invoking increasingly contrived scenarios. Why would an alien probe emit carbon dioxide? Perhaps as coolant. Why would it fragment? Perhaps intentional release of sub-probes. Why would it follow a hyperbolic trajectory through the system rather than entering orbit? Perhaps it was merely conducting a flyby reconnaissance. Each observation that fit naturally into the comet hypothesis required special pleading to accommodate into the artificial hypothesis. This pattern is characteristic of how incorrect hypotheses fail in science. They don't collapse suddenly under a single devastating observation, but gradually become untenable as each new piece of evidence requires additional assumptions to preserve them. The hypothesis grows more complex, more contrived, less elegant, until finally it is abandoned not because it's impossible, but because simpler alternatives explain everything just as well or better. The philosopher of science Imre Lakatos described research programs as having a hard core of fundamental assumptions surrounded by a protective belt of auxiliary hypotheses that can be modified as needed to accommodate new observations. A progressive research program generates novel predictions that can be tested. A degenerating one simply modifies the protective belt to accommodate whatever is observed without making testable predictions. The alien hypothesis for 3I-ATLAS showed signs of degeneration. It became increasingly flexible, able to accommodate any observation, and thus increasingly unfalsifiable. In contrast, the natural comet hypothesis made specific predictions. The spectrum should show cometary molecules. The brightness should increase and decrease in predictable ways as the comet approached and receded from the sun. The tail should point away from the sun. The non-gravitational forces should be consistent with outgassing. When these predictions were confirmed, confidence in the hypothesis grew. This is how science distinguishes between correct and incorrect explanations. Yet, acknowledging that 3I-ATLAS was almost certainly a natural comet doesn't diminish its significance. It remains only the third confirmed interstellar object ever detected, and the first interstellar comet observed with sufficient warning to conduct comprehensive observation campaigns. The data gathered will inform understanding of planetary system formation for years to come, providing a comparison point against which solar system objects can be contrasted. The differences in composition, that carbon dioxide dominance, those isotopic ratios, those dust properties, tell us that Planetary systems are diverse in their details, even while following similar overall patterns. The same physical laws operate everywhere, but initial conditions vary, and those variations propagate through the formation process to create systems that resemble each other as siblings resemble each other, recognizably related, but each with distinctive features. This diversity has implications for astrobiology, for understanding the environments in which life might arise. If comets deliver volatile compounds to terrestrial planets, as many scientists believe occurred on early Earth, then the specific chemistry of those comets matters. A planet receiving organic compounds from water-rich comets might have a different inventory of prebiotic molecules than one receiving compounds from carbon dioxide-rich comets. These differences could affect the ease with which life arises and the biochemical pathways it adopts. Similarly, the dust grains from interstellar comets contribute to the interstellar medium, the diffuse material filling the space between stars. When these grains are destroyed by collisions, by intense radiation, their constituent atoms are released and become available for incorporation into new generations of stars and planets. In this way, matter circulates through the galaxy, carrying information about stellar nucleosynthesis and planetary formation across light years and eons. 3IATLAS, in its brief visibility, became part of this grand cycle of cosmic recycling. Material that formed in one stellar system was now being distributed through ours, some of it eventually to be incorporated into future generations of planetary bodies. In a sense, every atom in the universe has been a traveler, moving from star to star, from dust grain to planet to dust grain again, across timescales that make geological ages seem brief. The philosophical implications stretch beyond astrobiology into questions of cosmic context and connection. The material in your body, the calcium in your bones, the iron in your blood, the carbon in your cells, was forged in stellar furnaces and scattered through space by supernovae. Some of it may have journeyed through multiple stellar systems before finding its way into the solar nebula that formed our sun and planets. You are, quite literally, made of stardust, and some of that dust may have been interstellar travelers, not unlike 3IATLAS. This perspective dissolves the artificial boundary between here and there in the cosmos. We are not separate from the universe, but part of its ongoing processes. The interstellar medium is not out there while we are in here. We are continuous with it, exchanging matter through comets and dust, connected by the same physical laws, participating in the same grand story of matter's evolution from simple hydrogen in the early universe to the complex structures that enable consciousness. 3IATLAS, then, becomes more than a scientific curiosity. It becomes a reminder of connection, a messenger not from elsewhere, but from the larger system of which our solar system is a part. Its arrival was not an invasion or even a visit in the usual sense, but rather a normal interchange in the ongoing conversation of matter and energy that is the galaxy itself. As December progressed and the comet continued to fade, public attention gradually shifted to other matters. The news cycle, always hungry for novelty, moved on to new stories. But for those who had followed the saga closely, who had watched the comet brighten and then dim, who had participated in the debates about its nature, something lingered. A sense of having witnessed something rare, a direct encounter with the reality of our galaxy as a dynamic system where objects flow between stellar systems, where the boundaries are permeable, where nothing is truly isolated. For the astronomers who had devoted months to observing and analyzing 3IATLAS, the work continued. Data analysis doesn't end when the object becomes too faint to observe. In many ways, it intensifies as researchers dive deep into the accumulated measurements, extracting every possible insight. Graduate students built careers on specific aspects of the comet's behavior. Theorists refined models to explain the observations. And always, in the background, preparations continued for the next interstellar visitor, because there would be a next one. The discovery of 3 interstellar objects in 8 years, Oumuamua in 2017, Borisov in 2019, and now 3IATLAS in 2025, suggests that such visitors may be relatively common, at least on astronomical timescales. As our detection systems improve, as more telescopes scan the sky more frequently, the discovery rate will likely increase. We may soon live in an era where interstellar objects are detected not once per decade, but multiple times per year. This normalization of the extraordinary may actually be healthy for scientific discourse. When each interstellar visitor was a unique, once-per-generation event, the temptation to interpret it as maximally exotic was stronger. But as the sample size grows, as we accumulate statistics on these objects' properties, patterns will emerge. We'll develop a baseline understanding of what typical interstellar comets look like, against which genuinely anomalous objects will stand out more clearly. Perhaps in this future, when an interstellar object genuinely exhibits properties that resist natural explanation, the scientific community will be better positioned to recognize and investigate it. The false alarms like 3IATLAS, objects that initially seemed strange but proved natural upon closer examination, serve an important function. They train our detection systems, refine our analytical techniques, and calibrate our expectations against reality rather than speculation. This process of learning from false positives is not unique to the search for interstellar anomalies. It characterizes all areas of science where rare signals must be distinguished from noise and natural variation. Particle physicists searching for new fundamental particles must discriminate between genuine discoveries and statistical fluctuations. Neuroscientists looking for neural correlates of consciousness must separate real effects from experimental artifacts. The methodology is similar: careful accumulation of evidence, rigorous statistical analysis, replication by independent teams, and always maintaining skepticism toward conclusions that would overturn established understanding. In the case of 3IATLAS, this process worked as it should. Initial speculation gave way to systematic observation, which generated data that constrained interpretations, which ultimately converged on a consensus understanding. The alien hypothesis was never proven wrong in an absolute sense. Absence of evidence is not evidence of absence, but it became unnecessary, an extra assumption not required to explain the observations, and thus properly set aside by Occam's razor. Yet the experience also revealed areas where the process could improve. The rapid spread of simplified narratives through social media, the difficulty of maintaining nuance in public discourse, the tension between the tentative language appropriate for science and the definitive statements that media and public crave. These challenges persist and may intensify as scientific findings propagate even faster through ever more connected information networks. Perhaps future science communicators will develop better strategies for conveying uncertainty without undermining public trust, for explaining that we don't know yet is a legitimate and often appropriate scientific stance for distinguishing between wild speculation and evidence-based hypothesis testing. The 3IATLAS episode provided lessons in all these areas, lessons that hopefully will inform how the next interstellar visitor is presented to and understood by broader audiences beyond the specialist community. Education plays a crucial role here. A public better versed in scientific methodology, in statistical reasoning, in the provisional nature of conclusions drawn from incomplete data would be less susceptible to sensationalized claims and better able to evaluate competing interpretations. This doesn't mean everyone needs to become an expert in astrophysics, but rather that basic scientific literacy, understanding how evidence accumulates, how hypotheses are tested, how uncertainty is quantified, should be as fundamental as literacy in reading and mathematics. The wonder and excitement of genuine discovery need not be diminished by scientific rigor. Indeed, the real universe revealed through careful observation is far more fascinating than any premature conclusion. 3I-ATLAS, understood as a natural interstellar comet carrying pristine material from another stellar system, formed billions of years ago under conditions unlike those in our solar system, traveling for eons through the galactic void before chance brought it through our neighborhood. This reality is extraordinary enough without embellishment. The patience required to build this understanding, to wait for observations to accumulate, to test hypotheses against data, is fundamentally at odds with the speed of modern information culture. Yet science cannot be rushed without sacrificing accuracy. Some questions require time to answer properly. Some phenomena must be observed through complete cycles. Some hypotheses need replication by independent teams. The rhythm of scientific discovery follows its own tempo, one dictated by the difficulty of extracting signal from noise, not by the cadence of news cycles. As you listen to these words in the quiet hours, perhaps you can appreciate that slower rhythm. The universe operates on timescales that dwarf human lifetimes. Stars form over millions of years. Planets cool and differentiate over billions. Light from distant galaxies has been traveling toward us since before Earth existed. Against these cosmic durations, the few months devoted to observing 3I-ATLAS represent barely an instant, yet within that instant, human ingenuity extracted meaningful knowledge from faint photons arriving across immense distances. The comet itself remains indifferent to our attention. It has no awareness of having been observed, no knowledge that intelligent beings detected its passage and debated its nature. It simply follows its trajectory, governed by gravity and the gentle push of outgassing, moving back toward the interstellar medium from which it came. In a few years, it will cross beyond the heliopause, that boundary where solar wind yields to interstellar medium, and become once more a citizen of the galaxy rather than a temporary visitor to our solar system. Will it ever pass through another stellar system? The probability is low but not zero. Space is vast and empty, stars separated by distances that even light requires years to cross. But over cosmic time, chance encounters occur. Perhaps in a few million years, 3I-ATLAS will fall into the gravitational well of another star, will once again experience heating and sublimation, will shed its ancient ices into alien skies where perhaps other beings, other intelligences, will observe and wonder about its nature and origin. Or perhaps it will wander the galactic disk for billions of years, without ever encountering another star closely enough to be significantly perturbed. Perhaps it will gradually lose all its volatile ices to the rare photons and cosmic rays that penetrate even interstellar space, becoming just a dark, inert fragment of rock and refractory minerals, invisible, undetectable, its story of formation and travel recorded only in crystal structures and isotope ratios that no one will ever measure. Both fates are possible, and both are equally valid endpoints for this traveler's story. The universe writes countless such narratives, most never witnessed, never recorded, playing out in darkness without audience or meaning beyond the simple physical processes involved. We were fortunate to glimpse one such story, to have our instruments sensitive enough and our survey programs systematic enough to notice this faint visitor before it departed. Future improvements in detection technology will likely reveal more interstellar objects, perhaps many more. Wide-field survey telescopes coming online in the next decade, instruments like the Vera Rubin Observatory, with its ability to image the entire visible sky repeatedly, will discover objects far fainter and at greater distances than current programs can detect. The census of interstellar visitors will grow from 3 to dozens to potentially hundreds, each offering a data point in understanding the properties of small bodies throughout the galaxy. With larger samples, statistical analyses become possible. What is the size distribution of interstellar objects? What fraction are ice-rich comets versus rocky asteroids? Do they show compositional patterns suggesting they originate primarily from certain types of stellar systems? How often are they ejected during planetary system formation versus later dynamical instabilities? Each question requires sufficient statistics to answer, and 3IATLAS, while valuable, represents just one point in what will eventually become a rich data set. This prospect of future discoveries should temper disappointment that 3IATLAS raised questions it couldn't fully answer. It was never going to be possible to completely characterize an interstellar object from distant observation alone. The light travel time, the faintness, the brief window of visibility all conspire to limit what can be learned. But each visitor teaches us something, refines our understanding incrementally, prepares us to better interpret the next one. Eventually, humanity may mount missions to intercept interstellar objects, not merely to observe from afar, but to encounter them directly. The technical challenges are formidable. Matching velocities with an object moving at tens of kilometers per second relative to the Sun requires propulsion capabilities beyond current spacecraft technology. But several mission concepts exist that could, with sufficient development time and resources, achieve such rendezvous. The scientific return would be extraordinary. Direct sampling of material from another stellar system, high-resolution imaging revealing surface features and structures, measurements impossible from Earth-based or even space-based telescopes, limited by distance. Such a mission would need extremely rapid development and launch capabilities, since the warning time between detection and closest approach is measured in months, not years. A standing rapid response capability with spacecraft pre-built and ready for customization and launch when an appropriate target is detected might be necessary. The cost would be substantial, but balanced against the unique opportunity to study material from another stellar system without the expense and difficulty of actually traveling to other stars, such missions might prove cost-effective. 3IATLAS discovered with months of warning before perihelion, would have been a candidate for such a mission had the infrastructure existed. A spacecraft could have been launched to rendezvous with it near Mars, conducting close-range observations during the period of maximum activity. The images and spectra obtained would have resolved many uncertainties that remained in ground-based observations. The composition could have been measured definitively rather than inferred from remote spectroscopy. The nucleus structure and rotation state could have been determined directly, but such capabilities remain aspirational rather than operational. The infrastructure, the pre-built spacecraft, the rapid launch capability, the mission operations expertise does not yet exist and may not for many years. In the meantime, we remain dependent on remote observation, on teasing out what information we can from faint photons gathered across millions of kilometers. This limitation is frustrating, but also, in a way, appropriate. It ensures that each discovery retains some mystery, some questions left unanswered, preserving the sense of wonder that drives exploration. The philosophical dimension of 3IATLAS deserves final reflection before we conclude this journey together. Throughout human history, we have struggled with questions of cosmic significance. Are we alone? Is life common or rare? Does intelligence arise frequently, or are we perhaps the only conscious observers in our galaxy? These questions cannot yet be answered definitively, but objects like 3IATLAS provide relevant data, however indirect. The chemistry it carries, the organic molecules potentially present, the processes that formed and shaped it, all bear on the question of life's cosmic context. If complex organic chemistry is common in interstellar objects, if carbon compounds form readily in protoplanetary disks around many different types of stars, then the chemical preconditions for life may be widespread throughout the galaxy. This wouldn't prove life is common. The leap from organic chemistry to actual living systems is profound and poorly understood, but it would suggest that at least the raw materials are available in many locations. Comets like 3IATLAS, if they deliver these materials to terrestrial planets, as they apparently did to Earth, could serve as vectors for distributing life's chemical building blocks throughout stellar systems. Conversely, if interstellar objects prove to be chemically simple, lacking complex organic molecules, despite their ages and the processing they've experienced, it might suggest that the chemistry leading to life requires specific conditions that are less common than current theories assume. Each measurement, each new interstellar visitor characterized, adds data to this grand question, building statistical understanding of what is typical and what is rare in the galaxy's chemistry. The absence of any obvious technological signature in 3IATLAS, no radio signals, no geometric structures, no behaviors inexplicable through natural physics, also informs the search for extraterrestrial intelligence. If technological civilizations commonly send probes to explore neighboring stellar systems, and if those probes remain operational for the millions of years required for interstellar travel, then we might expect to occasionally detect such objects passing through our system. The fact that 3 confirmed interstellar visitors have all appeared natural suggests either that such probes are rarer than some speculation imagined, or that they are sufficiently well camouflaged or subtle that they escape recognition. This is not to say we should cease looking for potential technosignatures in unusual objects. The scientific method requires considering multiple hypotheses and testing them against evidence. But it does suggest that the baseline expectation should be natural origin, with the burden of proof falling on claims of artificial construction. Extraordinary claims require extraordinary evidence, and that standard was not met for 3I-ATLAS. The natural comet explanation sufficed, requiring no additional assumptions beyond known physics and chemistry. As the years pass and 3I-ATLAS recedes into invisibility, its legacy will be the data it provided and the lessons it taught about conducting science in the public eye. Future interstellar visitors will benefit from improved observation strategies developed during the 3I-ATLAS campaign. Rapid response protocols will be refined, analytical techniques will be sharpened, and perhaps most importantly, communication strategies will evolve to better convey the excitement of genuine discovery while maintaining appropriate epistemic humility about what can and cannot be concluded from limited observations. The comet also reminded us that the universe is dynamic, not static. Our solar system is not sealed off from the galaxy, but constantly exchanges material with it. Every year, tons of interstellar dust drift through, too diffuse to easily detect, but present nonetheless. Occasionally, larger objects, comets and asteroids, wander through, some bound by chance into orbits around our sun, others like 3I-ATLAS just passing through. We live in a cosmic neighborhood where the traffic, though sparse, is perpetual, a quiet reminder that boundaries between here and there are more conceptual than physical. And so we come to the end of our journey through the story of 3I-ATLAS, that interstellar visitor that sparked such intense interest during its brief visibility. It arrived from darkness, passed through our neighborhood while we watched and wondered and debated, and has now returned to darkness, carrying its secrets back into the galactic void. We learned from it what we could in the time available, and though many questions remain unanswered, the knowledge gained justified the effort expended. Perhaps the most valuable lesson is the simplest. The universe is under no obligation to be easily understood. It presents phenomena that resist immediate categorization, objects that behave in ways that challenge our models and assumptions. Our task as conscious observers is not to force nature into comfortable categories, but to adjust our understanding to accommodate nature's complexity. 3I-ATLAS did not behave exactly as familiar solar system comets do because it wasn't one. It formed elsewhere under different conditions and carried that difference in its composition and behavior. Accepting this diversity, this variety in nature's expressions, is fundamental to scientific maturity. The universe is vastly larger and older than our direct experience, and the conditions under which matter and energy interact vary enormously across that space and time. What is common in one stellar system may be rare in another. What forms easily under one set of conditions may require extraordinary circumstances elsewhere. To expect uniformity across such variety would be naive. To celebrate the diversity is to appreciate the richness of cosmic evolution. As sleep draws closer, let these thoughts settle gently into consciousness. Somewhere out there, far beyond the reach of our telescopes, 3I-ATLAS continues its journey. The sunlight that briefly warmed it has faded to a distant point among countless stars. Its ices have returned to dormancy, frozen in the cold of interstellar space. It carries no memory of its passage through our solar system, no knowledge of the attention it received or the debates it sparked. It simply is a fragment of matter following the laws of physics through the vastness of space. And yet, because we observed it, because we directed our instruments and our intellect toward understanding it, 3IATLAS has become more than just a physical object. It has become part of human knowledge, woven into our growing understanding of the galaxy we inhabit. The data collected during those months will be analyzed and reanalyzed for years, appearing in papers and dissertations, contributing to models and theories, informing decisions about future missions and observation strategies. In this sense, the comet's passage through our solar system marks a permanent change, however small, in humanity's collective understanding of the cosmos. Future generations may look back on this era as the beginning of interstellar object astronomy, when these visitors transitioned from theoretical possibility to observed reality to routine discovery. They may find our initial confusion and speculation about objects like 3IATLAS quaint, much as we smile at early astronomers who thought comets were atmospheric phenomena. But they will build on the foundation we are establishing, using our early observations to calibrate their more sophisticated instruments and theories. The story of 3IATLAS is, in the end, one chapter in a much longer book that humanity is collectively writing, the story of how a species confined to one small planet learned to understand its place in a vast galaxy. Each observation, each discovery, each hard-won piece of knowledge adds to this larger narrative. And though individual contributions may seem small, together they accumulate into genuine understanding, into a scientifically grounded appreciation for the universe's scale, complexity, and beauty. So rest now, knowing that while you sleep, the universe continues its ancient dance. Objects like 3IATLAS drift through the darkness, whether observed or not. Stars shine, planets orbit, galaxies wheel through space in their stately processions, and on one small world circling an ordinary star, conscious beings look outward with instruments and intellect, gathering light and extracting meaning, building slowly but surely a map of the cosmos and our place within it. The work continues, as it must, as it will, for generations to come. And each new discovery, each visitor from the depths of space, adds another verse to the endless poem of existence. The universe speaks in the language of light and motion, gravity and chemistry, and we are learning, slowly, to listen and to understand. Sleep well beneath stars whose light carries stories from distances and times beyond imagining, part of a cosmos far grander than any fiction, more mysterious than any speculation, and infinitely worthy of our wonder, our curiosity, and our patient, careful study.